For some fixed integer n, show that a relation R on the set of integers Z defined by the ordered pair A comma B belonging to R if and only if n divides A minus B as an equivalence relation on Z. Okay, let us begin. So here we have a fixed integer n and we have a relation R on Z. The relation R on Z, this is simply telling us that R is a subset of the Cartesian product of the set of integers with itself. And the relation R is defined as R as a set of ordered pairs A comma B such that A and B are both integers and we have n divide A minus B. So n is dividing A minus B. So this is the relation that is given to us and we have to verify whether if it is an equivalence relation on Z or not. Now equivalence relation simply means that if a given relation is reflexive, it is symmetric and transitive, then it automatically is referred to as an equivalence relation. So let's quickly go through the definition of each of the types of relation. So let us suppose R is a relation on the set A. So R is a relation on the set simply means that R is a subset of the Cartesian product of the set A with itself. Then our relation R is going to be reflexive if and only if the ordered pair A comma A belongs to the relation R for all values of A belonging to the set A. Then R is going to be symmetric if the ordered pair A comma B belonging to the relation R implies that B comma A also belongs to the same relation R for all values of A and B picked up from the set A. And finally, R is going to be transitive if we have two ordered pairs A comma B and B comma C belonging to the R implies that A comma C also belongs to the relation R for all values of A, B and C picked up from the set A. Okay, we'll check each of them one by one. So let's start with the first one. R is reflexive. So here what we'll do, we are going to consider an arbitrary element A. So let A be an arbitrary element from the set taken from the set A such that we have the ordered pair A comma A belonging to the relation R. Now we're going to use the definition. So R is given by the ordered pair A comma B such that n divides A minus B, where n is some fixed positive integer. Now since we have A comma A, so we're going to replace this B with A. So here our definition must become n divides A minus A. Now n divides A minus A is also means that n divides 0. That's a true statement because n indeed divides 0. So here this is telling us that the relation R is going to be reflexive in nature. So this is a reflexive relation. Now let's go to the second one where we'll check whether if the relation R is symmetric or not. So here what we'll do, we're going to consider two elements, two arbitrary elements A comma B, which belongs to the set A such that we have, so here I would like to make a quick clarification. So our relation is defined on the set of integers. Although I have here chosen the set A, this is actually A is nothing but the set of integers Z. Okay, so here, so A and B are elements from the set A, or we can say that, or in other words, we can simply say that A and B are both integers such that if we consider A comma B belonging to the relation R, then according to the definition of R, this means that n divides A minus B. Now if we say that n divides A minus B, in other words, we can say that A minus B is a multiple of the fixed integer n. So here we can say A minus B equals to lambda times n, where there exists some lambda, some unique value of lambda belonging to the set of integers. So now what we'll do, we're going to multiply both sides with -1 to get B minus A. So B minus A equals to negative lambda multiplied to n. Now lambda is an integer, so negative lambda is also going to be an integer. So here what we have shown that B minus A is a multiple of n. So can we not say that n divides B minus A? Now n dividing B minus A, that's the definition that B comma A, the ordered pair B comma A belongs to the relation R as well, which means that our relation R is going to be symmetric as well. It is a symmetric relation. Okay, so if you're confused with this is where always go back to the definition. So we considered R to be the set of ordered pairs A comma B. So if we consider the set of ordered pairs B comma A All you have to do is replace a with b and b with a, and that would simply mean that n divides b minus a. Now this is what we mean when we say that n divides b minus a. It also means b comma a belongs to the relation R. So here we have showed that the relation R is symmetric. Now we will finally show that the given relation R is also transitive. Now to show that it is transitive, we need three elements. So let's consider three elements, a, b, and c. These three elements are all integers. So all integers such that if we consider the ordered pair a comma b belonging to the relation R and another ordered pair b comma c belonging to the relation R, we must be able to show that a comma c also belongs to R. This is going to be our goal. We have to show that a comma c belongs to the relation R, or in other words, we have to show that n divides a minus c. This is what we need to show. So let's try to show that. So a comma b belongs to R according to the definition means n divides a minus b. And b comma c, the ordered pair belonging to R, simply means that n divides b minus c. Now n dividing a minus b can be also thought of as a minus b equals to some multiple of n. So here we will consider alpha times n. And n dividing b minus c can be thought of as b minus c equals to some beta times n, meaning b minus c is a multiple of n. Where we can say where alpha comma beta, these are integers, some integers. We don't have to worry about the value. Now what we'll do, we're going to isolate b from here. So b is going to be equals to a minus alpha times n, and we're going to substitute this value in the second equation. So we get a minus alpha times n minus c equals to beta times n. Rearranging the terms, we get a minus c equals to alpha plus beta multiplied to n. Now alpha and beta being integers, so their sum is also going to be an integer. So here what we have shown that a minus c is a multiple of n. Now in other words, what we have found out here is that n divides a minus c. That's what we needed to show. N divides a minus c. In other words, we are saying that the ordered pair a comma c also belongs to the relation R. So we started out by considering two ordered pairs, a comma b and b comma c, belonging to the relation R. And we are able to show that the same ordered pair a comma c also belongs to the relation R. So R is transitive in nature. So this is a transitive relation. Now since our relation R is reflexive, it is symmetric, as well as it is transitive, thus we can say thus our relation R is an equivalence relation. This is an equivalence relation on the set of integers z, hence proof.